Hi there. In this demo video, I'm going to demonstrate the functionality of the project that I've done for AWS IoT challenge. So in this project, I use the accelerometer sensor as well as a number of other sensors to create an embedded device that sends that data over to the AWS cloud and visualizes that data. And it was a very interesting experience recording that 3D acceleration data and kind of analyzing it on the AWS platform. So this is the overview of the hardware that I used. Here is an embedded Linux device that is in constant communication with the AWS cloud, and here's the battery, and this is a fully portable solution. And here is the platform I used for the sensors that communicates with the embedded Linux device. So I'm gonna jump in and show you the data that I collected. This data was collected live from a travel that I made to the grocery store. The full length of travel was about 23 minutes, and this is what the data looks like. So the orange line is the z-axis acceleration data. The dark blue one is the y-axis acceleration data. And finally, the x-axis acceleration data is represented by this light blue line. And this is how the accelerometer was placed on the moving vehicle. So if the vehicle moves forward, the passengers will experience a push to the seat, and that's represented as a positive acceleration. If the vehicle stops, then you experience a force pushing you forward. That's a negative acceleration. And similarly with the y-axis, if you make a right turn, you experience a force to pushing you to the left. So that's registered as a negative acceleration on the y-axis. So anything that represents a negative y value means a right turn, and that's quantified depending on how sharp the turn was. And the same way with the positive y value and the left turn. And finally, the x and y axis. So there's a constant positive acceleration registered on the z-axis because of the gravity, and anything that pushes you further to the bottom of your seat, that adds to that positive z value, and anything that makes the passengers feel weightless, that would register as a negative z value. So if at any point the z-axis crosses the x-axis, or the z value, the acceleration, the z-axis crosses the x-axis, that means there was a moment where weightlessness was experienced in the moving vehicle. So this is the data. Up to this point, the vehicle was stationary, and I was actually parked in the ramp. That's where you see a slight negative value registered on the x-axis. This was a ramp, so I was facing down on my ramp, and here is where the vehicle started moving, and right away you can see at this point there was a brake, so there was a negative acceleration experienced here. Here again there was a negative acceleration, so this was actually a stop sign, the first stop sign that I encountered. This was a right turn that I made after that stop sign, because you can see a negative y value being registered here. There was another stop sign where I was about to enter the actual street. So this is that second stop sign. You can see a brake, and this one is actually a very sharp left turn that I made into the main street. So you can see how easy it is to kind of, looking at this data, kind of figure out valuable insights from that driving. So for example, how sharp were the turns or how sharp were the brakes. And finally, the z-axis can show you how bumpy the ride was or if it was a smooth ride. And this continues. Here you can see a very sharp brake at this point. Here you can see a moment of constant positive acceleration and very smooth ride. And if you continue, the amount of brakes are generally the quantity of brakes, they're larger because you accelerate over time, but when you brake, you have to stop instantly. So that's why you see these sharp falls in the graph on the x-axis. And if we keep going, here you can see some very sharp turns. So this would be a left turn here, excuse me, a right turn, indicated by a negative force on the y-axis. And finally here you can see a very big bump, which accumulated up to close to 15 Gs. So that was a pretty tough bump right there. And this is what the whole data looks like. And this was for a 23-minute drive. Finally, I have some other graphs that show the different metrics. So here you can see the maximum value of z, y, and x over the whole period of the drive. So the biggest one is z, but that's also because you have to account for the 9.8 Gs for the gravity. The second one after that was the y force. So the positive y again indicates a left turn. So if you compare that with the minimum value, this would represent the amount of right turns. This would represent this would quantify the number of brakes or the vehicle moving backwards. So you can compare that with the maximum, and you can see right away that the acceleration experienced in the negative direction was more, which represents the sharp brakes as opposed to smooth accelerations. And finally, the negative z data. Again, this is you have to deduct 10 from this. If you do, you get a negative value, and that's the g-force, the net g-force that was experienced in the vehicle. And finally, throughout all this, I'm also capturing the temperature data in real time. This is also more for safety purposes. Since all of this data is being monitored in real time, it's possible to send real-time notifications. For example, in the case of extreme temperature, which I've actually implemented in this project, you can send a text message to a specific phone number. Furthermore, in the case of unusual acceleration data, for example, if the z value crosses the x line, that's a pretty unusual g-force. Or if any of these go above anything above 10 Gs, that's a pretty unusual force that's experienced. So that could indicate a very dangerous accident that the car may be in. So all of that is being monitored in real time, and all of those functions can be implemented. And this one shows the overview of the architecture. So this is the Omega 2, which is the embedded Linux device. Here's my sensor. Those are in constant communication. The Omega 2 is in constant communication with the AWS IoT. Here's the IoT platform. And here I have two rules. One is for an emergency notification monitoring the temperature. One is the one in charge of ingesting the IoT data and storing it in an S3 bucket, as well as pushing it forward into a Amazon Firehose, so that way the data can be batched. So that would be the IoT source, and this is the IoT source, data sources stream, which is storing data in a S3 bucket, and at the same time is pushing it forward to Kinesis Analytics for further analysis and real-time analysis. And here I have further 3 more fire hoses, batching the data into CSV objects and storing it on the S3. And these are the rest of the fire hoses that you can see here. One for the full data, one for aggregate XYZ values, and one for aggregate temperature. And these 2 are measured per minute. And this is my S3 bucket that stores all the data. And finally, you have the Amazon QuickSight, which visualizes the data for the user. And as you can see, you can create multiple graphs and different visualizations and analyze the data in different ways. So thank you so much for listening. If you have any questions, please let me know. Thank you.